Hello 10th class students, as we have finished the atomic structure chapter, now what we are going to do is we are going to start with the periodic classification of elements. When it comes to intermediate, these two chapters repeat: atomic structure and periodic classification of elements. So these videos are going to help you with this periodic classification of elements, better understanding of this particular chapter. So watch them and make sure that you watch them again and again and again, because these videos are the animated versions of the chapter, and therein you can easily understand what exactly the chapter explains. Is the same thing you are going to watch in the television screen also. Thank you.
By now, we are aware of the difference between elements, compounds, and mixtures. Do you remember the differences? Mixtures are like food items that we consume. They contain everything in proportion that we desire. We can add or remove a substance according to our need. Compounds, on the other hand, are those which have substances in fixed proportion. So if you change the proportion of substances, it will affect the compound and render it changed. For instance, if you remove even one hydrogen from H2O, that is water, the composition changes and water as a compound does not exist. Thus, fixed proportion is a must in compounds. Lastly, we have the elements. These are the purest forms of any known substance. They are composed of only the same type of atoms. There are neither proportions nor random mixing of substances. So can we say that compounds and mixtures are made up of elements? Absolutely. So in nature, it implies that elements are the basic forms of every material that we find around. And hence, in order to study every substance around us, we need to begin with studying the various elements. So where do we begin? Maybe the reactivity or maybe the physical properties first, right? I'm asking if we can study the reactivity and physical properties of each of the elements. Is that feasible? Well, all these would have been valid only if the elements would be few in numbers. Do you know the number of elements that exist? Astonishingly, the number of elements that we find naturally occurring is 98. While the total number of elements known to mankind is 118. So how do we study each element individually for all its properties? Looking at the number of elements that exist, I don't think it would be convenient to pick every element individually and study all the properties, right? Imagine you have to organize the kitchen. You will not place any vessel or eatable randomly anywhere. You will organize the shelves and refrigerator in the most convenient way which is suitable for your needs. Similarly, for studying so many elements, we need to organize them appropriately. An organization begins with arrangement. Yes, arranging the various elements is the first step towards understanding their properties. And arrangement is possible only if we categorize them, right? This is how we organize the elements. And this process of categorization helps us study the elements with ease. In other words, we've classified the elements here. Classification of elements is categorizing the various elements into groups based on similarities and differences in their properties. The classification system helps us in grouping the various elements into categories, which we refer to as the periods. Hence, the system is also referred to as the periodic classification of elements. Let's get to know how periodic classification was carried out in the early days of emerging chemistry when not many elements were known to people. In the upcoming videos, we will understand the various classification systems put forth by the different legendary personalities. It was around the beginning of the 19th century that a famous German chemist attempted classification of the then known elements. It was none other than Johann Wolfgang Dobereiner who did so. He classified the elements known at that time in a particular manner. He placed them into groups having 3 elements each. Do you think these groups of 3 will have elements arranged randomly? Of course not. What's the unique way of placing these elements then? It's simple. Dobereiner arranged the set of 3 elements in such a way that the average of atomic mass of first and third element in the set gave him the atomic mass of the middle element. In simple words, the atomic mass of the second element will be approximately equal to the average of atomic masses of the first and the third element. Let's take an example to understand this better. One of the triads he suggested was that consisting of lithium, sodium and potassium. The atomic mass of lithium is 6.9 while that of potassium is 39. So if you take their average, what would you get? Yes, you get 23, and 23 is the atomic mass of sodium. And this is exactly what Dobereiner had in mind when he framed the triads. However, this is not a perfect method of classification because not all elements follow this principle when arranged in triads. Also, when Dobereiner had put forth the system, only a few elements were known to him. With the discovery of newer elements, this system of grouping elements didn't really work. After grouping the elements in a series of 3, there came a system in which the elements were grouped in series of 8. Yes, this system was put forth by an English scientist named John Newland in the year 1866. There were around 56 elements that Newland could group. He simply arranged the elements in an increasing order of their atomic masses. At the end, he realized that these could be grouped such that every 8th element resembled the first. Astonishingly, the arrangement also stuck an analogy in his mind. Well, can you guess what analogy popped in Newland's mind? Let me help you with that. These are like octaves. Yes, octaves found in music. In case of octaves, we find that every 8th note is same as that of the first one. He found that every 8th element in the series resembles the first in various ways. This is how Newland arranged the elements in a table. For instance, as we can see here, if we consider lithium, then the 8th element after it would be sodium. You would be amazed to know that they both share similar properties. Next immediate examples would be that of beryllium and magnesium. Even these are at positions such that magnesium is 8 places away from beryllium. And yes, they both do resemble each other. With this analogy, Newland named the grouping system of elements as laws of octaves and even Newland's laws of octaves. Although the arrangement pattern was quite good, but it was valid only until calcium and not applicable for elements after that. After calcium, every 8th element did not have properties similar to that of the first. By that time, there were only 56 elements known. Newland assumed that more elements will not be discovered in the future. Many elements were of course discovered later, but did not have properties that could fit in the system in any possible way. Another notable drawback in this system was that cobalt and nickel were placed in the same position. And this position was in the group of halogens like fluorine, chlorine and bromine. But these halogens have completely different properties as compared to cobalt and nickel. With all these limitations, Newland's octaves also had to be ruled out. Later, there came a proper, well-defined system which was put forward by a famous Russian chemist called Mendeleev. He not only gave a systematic approach to classify elements, but even laid the foundations of modern periodic classification that is widely used today. Let's have a detailed look at the periodic classification of elements as presented by Mendeleev in the next video. Dmitry Ivanovich Mendeleev played quite a legendary role in the field of chemistry. He not only gave us the simplest and the most efficient method of grouping elements, but also laid the foundations of periodic classification of elements that we use today. So in this video, let's dedicate some time to understand what and how Mendeleev actually worked on. When Mendeleev began his work of grouping the elements and arranging them, there were almost 63 elements known to him. He was firm on the thought of arranging the elements with respect to their physical as well as chemical properties. He knew that for understanding the chemical properties, he would need to make them react with one or two standard elements. For this, he chose hydrogen and oxygen. But why? Mendeleev thought of making the elements react with hydrogen and oxygen because of the following reasons. They are very reactive, they are found readily, and they form compounds with most of the elements. Yes, this helped him understand the chemical properties of all the reacting elements. Later, in order to simplify the process, he wrote all the physical and chemical properties of each element on 63 different cards. Now, all he had to do is arrange these cards. But that wasn't so simple. So he started arranging the cards in the increasing order of their atomic masses. When he was done pasting all these cards on his wall, he had two astonishing observations. One was that there were a few empty spaces left in the complete table that he formed. These positions belonged to the elements that were not yet discovered. But Mendeleev had a firm belief that the missing elements did exist and are yet to be discovered. Not only this, but he was so confident about the characteristics of these elements that he predicted their properties well in advance. Later on, when the elements were discovered, it was found that the properties predicted by Mendeleev were almost a perfect match. Second observation that Mendeleev had was the recurrence of the physical and the chemical properties of these elements. When arranged in a systematic manner, it was found that the physical and the chemical properties of elements recurred at a particular interval of frequency. With this, Mendeleev came up with a law. He named it as the periodic law. The law stated that properties of elements are periodic functions of their atomic masses. Now, what do we exactly mean by this? Let's simplify this by breaking the statement in parts. Properties of elements means the physical and the chemical properties of all the elements in the table. Are the periodic functions means those which occur at regular intervals. And lastly, of their atomic masses means when arranged in the increasing order of their atomic masses. So can we simply say that when elements are arranged in the increasing order of their atomic masses, they show similarities in the physical and chemical properties at regular intervals? Yes, that's what Mendeleev meant. This is how Mendeleev laid the foundations for the modern periodic table. But did this great contribution by Mendeleev have no limitations at all? Well, there were a few that emerged with time. Let's discuss the achievements and the limitations of Mendeleev's work in the next video. The periodic table put forth by Mendeleev was quite well defined, but it wasn't the best table ever. Why do I say so? It's because with time, the number of elements being discovered increased, and fitting them into the table according to the periodic law by Mendeleev seemed difficult. Also, we have taken a look at the major limitations of the periodic table by Mendeleev. So with all these limitations, how do we study the elements? How do we carry out the periodic classification? Well, if the elements discovered later did not follow the periodic law given by Mendeleev, then the only way to arrange them was by modifying the law. Yes, this was, however, not what scientists could think of as the first step. It was quite gradually that the scientists realized the fact that the law could be modified. But how did this happen? It was around 1913 that the British physicist Henry Moseley found an interesting fact. He realized that instead of atomic mass, all the elements will show periodicity if arranged on the basis of their atomic numbers. Wait a second, did I just say atomic number? Isn't atomic number a randomly assigned number to the atom by us? Actually not. Atomic number of any element is never a randomly assigned number. It is basically the number of protons present in the nucleus of the atom of that element. For instance, let us consider the first 4 elements in the table. So we get atomic numbers of hydrogen as 1, helium as 2, lithium as 3, and beryllium as 4. So why are these elements assigned these particular atomic numbers only? Can we change these numbers ever? No, we can't. That is because they have these respective numbers of protons in their nuclei. Hydrogen has just one proton in its nucleus. Similarly, helium has 2 and lithium has 3. And how many protons will beryllium have? Correct, it has 4 protons. The same is valid for other elements as well. Coming back to the table, did Henry Moseley think that characteristics of elements are based on their atomic numbers and not their atomic masses? Yes, that's what he meant. And with this, there emerged a new law of studying the periodicity of elements. It was called the modern periodic law. The law stated that the properties of elements are periodic functions of atomic numbers. So what does this mean? This means that the physical and chemical properties of elements do occur periodically. But this happens when the elements are arranged according to their atomic numbers. All the known elements could be arranged based on their atomic numbers. With this, predicting the properties of elements yet to be discovered got simpler and more precise. This helped in placing the newly discovered elements properly in the periodic table. Also, overcoming the limitations of Mendeleev's table was another advantage. And how did that happen? Do you remember the limitations? The first limitation of no precise position for hydrogen was mainly overcome. It was assigned a position that would not lead to any confusion. We will take a detailed look at this position of hydrogen later in the higher grades. Next limitation of the Mendeleev's table was the position of isotopes. Can you recollect what isotopes are? Yes, they are the atoms of the same element with different number of neutrons. That is the reason why, in spite of belonging to the same element, the atoms have different atomic masses. Because atomic mass is the sum total of all the protons and neutrons present in the nucleus. Placing isotopes in the table was a limitation. But as we know, in the modern periodic table, the position of elements was no longer based on atomic masses. They were based on atomic numbers. An atomic number is given by the number of protons. That means the different number of neutrons will not be a worry for us. So it was possible to place the isotopes now. Because all the isotopes of any particular element could be placed at one single place. And this place would be the position of that element in the table. So now can we say that chlorine 35 and chlorine 37 will be placed together? They both have 17 protons, which means they will have the same atomic number. Hence, they will be placed together. Lastly, we had the prediction and placement of undiscovered elements. The previous table by Mendeleev was based on atomic masses of elements. However, the atomic masses of elements were not arranged in a constantly increasing order. Hence, if newly discovered elements were to be placed in the table, then their position would be confusing. But why? It's simply because if the atomic masses of previously discovered elements were not in a regularly increasing manner, then how and where will we place the new ones? Just for the sake of understanding, let us assume some values for the atomic masses of two elements. Element 1 has atomic mass 300, whose position comes first, while element 2 has an atomic mass 297, which is placed later in the table, that is, after element 1. Now in this case, if a newly discovered element, say element 3, has atomic mass of 299, where will we place it? Between the two elements or after the second element with atomic mass 297? And this is what was happening with Mendeleev's periodic table because the atomic masses of elements were not placed in a constantly increasing manner. Some elements did have atomic masses less than the previously placed element. So placing the newly discovered elements will disturb the entire table. But in the modern periodic table, the position of elements was based on atomic numbers. So newly discovered elements could be easily added in between. Because the atomic numbers of elements are found to occur in a constantly increasing manner. This is how the important limitation of Mendeleev's periodic table got ruled out. And that is the reason why the new periodic table surfaced as the most useful tool for studying elements. The newly arranged table of elements was based on the modified law. Do you remember the name of this important law? Yes, it is the modern periodic law. So can you guess the name of the table that was based on this law? Yes, it was called the modern periodic table. Now let's have a detailed look at this modern periodic table, its properties, and a few of its important characteristics in the upcoming videos. Chemistry gives answers to many queries. It acts as a bridge between the theoretical concepts and the practical world. However, where does chemistry get all the answers from? How do the reactions change everything around us so drastically? Well, the answers are stored inside the small nuclei of atoms. Yes, the tiny nucleus inside every atom is like a treasure box. It holds the mystery of several reactions. Now the next question to pop in our mind is, how does the nucleus of a single atom define the reactions in which the atom is participating? That's right. It's the subatomic particles in the nucleus, the protons and the neutrons that are the influencing factors. Yes, the presence and the number of protons and neutrons in the nucleus of any atom define many important characters like the atomic number, atomic mass, isotopic forms, and so on. Wait a second. Do we know what these are? What do we mean by atomic number? How is it different from the atomic mass, and what exactly are isotopes? Let's begin with the atomic number first. Atomic number is denoted by the letter Z. As the name suggests, atomic number means the number assigned to a particular atom. Now I want you to think, on what basis should an atom be assigned a number? Should it be on the basis of when the atom was discovered, or on the basis of how much quantity of the element is present in nature? What factor can be applied for numbering the atoms or the elements in general? One promising way is by numbering based on the number of protons present inside the nucleus of the atom. Yes, it's because the atom of every element has fixed number of protons in its nucleus. And this number is unique to every element, right? What do we mean by this? For example, any atom of oxygen always has 8 protons in its nucleus. No other element has atoms with 8 protons in it. That means the number of protons in the nucleus of an atom is like the identity of that element. So can we number the atoms or elements based on the number of protons in the atomic nucleus? Yes, this is how atomic numbers are defined. Atomic number, in simple words, is the number of protons present in the nucleus of the atom. Why do we need an atomic number, by the way? The atomic number helps in defining the characteristics of the element. And why so? Just think about it. We know that the number of electrons is equal to the number of protons in an atom. We also know that the number of electrons will determine the valency and thus the reactive capacity of an atom. So now can we connect the dots? Yes, the characteristics of elements will include a few properties. And these properties will be based on the reactivity of the atoms, right? We also know that the reactivity depends on the number of electrons present in the atom. And the number of electrons is the same as the number of protons. So this is why the characteristics of atoms are largely dependent on the atomic number. That is the reason the atomic number, or simply the number of protons, is important to us. Well, we know that atoms are the fundamental units of every matter. So can you guess what could the size of a single atom be? And do all the atoms of different elements have the same atomic size? Let's study the concept of atomic size in detail in the next video. In the previous video, we have seen how atomic mass is measured. Now let's understand atomic mass in detail. Before that, can you tell me what exactly the concept of atomic number is? Can you define it once for me? Yes, it's simply the number of protons present inside the nucleus of an atom. Now, on similar lines, can you tell me what atomic mass could be? Yes, it simply means the mass of an atom. But how does it get determined? Imagine we have a bag which is made up of extremely thin material. So thin that it almost does not have any mass of its own. Now we fill this bag with some stuff inside. If this bag is placed on a weighing scale, then can we say that the total mass of the bag will be the sum of the mass of all the objects inside it? Absolutely. Similarly, the mass of an atom can be calculated with the help of the subatomic particles in it. But we know that among all the subatomic particles, electrons have negligible mass. That is, they are considered to be almost weightless. So what are we left with? Yes, we have both protons and neutrons in the nucleus. And these two do have some amount of mass is what we know. Now tell me one thing, which among these two particles should be considered? Shall we consider only the mass of protons or only the neutrons? Or both together? Well, since both have a significant amount of mass, we will consider the mass of both together. Hence, the atomic mass is defined as the total number of protons and neutrons present inside the nucleus of the atom. It is also referred to as the mass number. Let us take a simple example. In case of a simple element like fluorine, we find that there are 9 protons and 10 neutrons in the nucleus. Wait a second. We have always come across cases where the atomic nucleus has an equal number of protons and neutrons. So how is it that the number of neutrons is more? Well, tell me, does the presence of additional neutrons really bother the atom? Does the charge of the atom increase or decrease? Absolutely not. That's because they're neutral. Then why should an extra neutron bother us? So coming back to the atomic mass of fluorine, we have 9 protons and 10 neutrons. That means the total would give us 19. So can we say that the atomic mass of fluorine is 19 units? That's right. Just like fluorine, even aluminium has an extra neutron compared to the number of protons. That is, in a single atom of aluminium, we have 13 protons and 14 neutrons. Summing up the two, we get 27 units, which is the atomic mass of aluminium. Now let's take another random example of chlorine. A chlorine atom has 17 protons and 18 neutrons. That means the atomic mass of chlorine will be 35 units, right? Absolutely. But wait a second. A few chlorine atoms that exist in nature exhibit a different form. Some of them have 17 protons and 20 neutrons. That gives us the atomic mass of chlorine as 37 units. So which one is the correct atomic mass? In case of chlorine, both the atomic masses are right. The atoms having 17 protons and 18 neutrons have an atomic mass as 35 units. On the other hand, chlorine atoms with 17 protons and 20 neutrons have an atomic mass of 37 units. But now the next question to pop up in our minds is, how can we have one element having two different kinds of atoms? And is this valid only for chlorine, or are there other elements also which exhibit this phenomenon? Let's find out more about this mysterious concept of isotopes in the next video.
The periodic table is instantly recognizable. It's not just in every chemistry lab worldwide. It's found on t-shirts, coffee mugs, and shower curtains. But the periodic table isn't just another trendy icon. It's a massive slab of human genius, up there with the Taj Mahal, the Mona Lisa, and the ice cream sandwich. And the table's creator, Dmitry Mendeleev, is a bona fide Science Hall of Famer. But why? What's so great about him and his table? Is it because he made a comprehensive list of the known elements? Nah, you don't earn a spot in Science Valhalla just for making a list. Besides, Mendeleev was far from the first person to do that. Is it because Mendeleev arranged elements with similar properties together? Not really, that had already been done too. So what was Mendeleev's genius? Let's look at one of the first versions of the periodic table from around 1870. Here we see elements designated by their two-letter symbols arranged in a table. Check out the entry at the third column, fifth row. There's a dash there. From that unassuming placeholder springs the raw brilliance of Mendeleev. That dash is science. By putting that dash there, Dmitri was making a bold statement. He said, and I'm paraphrasing here, "Y'all haven't discovered this element yet. In the meantime, I'm going to give it a name. It's one step away from aluminum, so we'll call it Eka aluminum. Eka being Sanskrit for one. Nobody's found Eka aluminum yet, so we don't know anything about it, right? Wrong. Based on where it's located, I can tell you all about it. First of all, an atom of Eka aluminum has an atomic weight of 68, about 68 times heavier than a hydrogen atom. When Eka aluminum is isolated, you'll see it's a solid metal at room temperature. It's shiny, it conducts heat really well, it can be flattened into a sheet, stretched into a wire, but its melting point is low, like freakishly low. Oh, and a cubic centimeter of it will weigh 6 grams. Mendeleev could predict all of these things simply from where the blank spot was and his understanding of how the elements surrounding it behaved. A few years after this prediction, a French guy named Paul-Émile Lecoq de Bois-Baudran discovered a new element in ore samples and named it gallium after Gaul, the historical name for France. Gallium is one step away from aluminum on the periodic table. It's Eka aluminum. So were Mendeleev's predictions right? Gallium's atomic weight is 69.72. A cubic centimeter of it weighs 5.9 grams. It's a solid metal at room temperature, but it melts at a paltry 30 degrees Celsius, 85 degrees Fahrenheit. It melts in your mouth and in your hand. Not only did Mendeleev completely nail gallium, he predicted other elements that were unknown at the time: scandium, germanium, rhenium. The element he called eka-manganese is now called technetium. Technetium is so rare it couldn't be isolated until it was synthesized in a cyclotron in 1937, almost 70 years after Dmitri predicted its existence, 30 years after he died. Dmitri died without a Nobel Prize in 1907, but he wound up receiving a much more exclusive honor. In 1955, scientists at UC Berkeley successfully created 17 atoms of a previously undiscovered element. This element filled an empty spot in the periodic table at number 101 and was officially named Mendelevium in 1963. There have been well over 800 Nobel Prize winners, but only 15 scientists have an element named after them. So the next time you stare at a periodic table, whether it's on the wall of a university classroom or on a $5 coffee mug, Dmitri Mendeleev, the architect of the periodic table, will be staring back.
Why does bond formation take place? Can you give me the answer? Yes, it takes place because atoms are always in a constant struggle to reach the stable state. And what is this stable state? Well, if the atoms have only one shell, then the stable state is achieved when 2 electrons are present in it. And if the atom has 2 or more than 2 shells, then the stable state is achieved when the outermost shell contains 8 electrons. It's called an octet. But the stable state is seen only in case of a few elements. We know that elements like helium, neon, argon, etc. have atoms with such desired electronic configuration. But what about the case of atoms which do not have this octet? Yes, they will participate in bond formation. That means they will either give or take or share electrons. But wait, who decides how many electrons will participate in the bond formation? Or who tells the atoms if they've to give or take electrons? Well, the answer to these questions is valency. Let's understand this concept in detail. In simple words, valency is defined as the combining capacity of an element. Now, what exactly do we mean by this? When we say combining capacity, that means how much can an atom bond with another atom. Does that mean how many electrons can be given or taken or even shared? Yes. Does the capacity of an atom to give electrons, accept electrons, or even share them in order to achieve the octet state can be termed as its valency. And what about the case of elements with just one shell? That's correct. Trading of electrons is carried out for attaining 2 electrons in the outermost and only orbital in such atoms. Let us take simple examples to understand this. In case of hydrogen, we have just 1 electron in the outermost shell. That means it has to somehow add 1 more electron to the outermost shell. Thus, we find that the valency of hydrogen is 1 as it accepts or sometimes even shares electrons with atoms of other elements. So, can you tell me the valency of oxygen now? The electronic configuration of oxygen is 2, 6. That means it has 6 electrons in the outermost shell. So, how many electrons are needed to complete the octet? Yes, 2 electrons. Thus, the valency of oxygen is 2. It accepts or takes 2 electrons from other atoms for completing the octet. Now tell me, what will be the valency of magnesium? We know that magnesium has 12 electrons. That means the electronic configuration of magnesium is 282. So how many electrons will be needed now? 6. That's correct. And that's what we're able to see. 6 electrons are needed to complete the octet. But which atom will give away 6 electrons so easily? Is it even possible? Not really. Then how will magnesium complete its octet? This is where the concept of donating electrons comes into the picture. If managing the gain of 6 electrons is difficult, then can it think of giving or donating the 2 electrons? Yes, absolutely. So if magnesium gives away 2 electrons from its outermost shell, then we say that the valency of magnesium is 2. That means it's not only about how many electrons can be taken, but also about how many electrons can be given by the atom. That is how we calculate the valencies of various elements. Now, to understand the concept better, let's take an example of elements forming one compound. Maybe we can think of sodium chloride. For the formation of one molecule, we need 1 atom of sodium and 1 atom of chlorine. What are the valencies of each, by the way? Sodium has the electronic configuration 281, while chlorine has an electronic configuration 287. Before I tell you what happens, I want you to give it a shot. What do you think will happen? Doesn't this indicate that sodium will donate 1 and chlorine will accept 1 electron to complete their respective octet state? Yes, that's absolutely correct. And that is what helps in the formation of sodium chloride molecule. Chlorine needed 1 electron which it got from sodium, and sodium gave 1 electron as it was the easiest way to achieve stability. So the valency of both sodium and chlorine is 1. Does this mean that only elements having the same valency always combine together to form a bond? Not really. Just take the simple example of a water molecule. We have seen that the valency of hydrogen is 1 while that of oxygen is 2. Here, hydrogen needs 1 electron while oxygen needs 2 electrons. Both need electrons. So how do the atoms combine in this case? How will the bond formation take place then? Well, they will both share electrons with each other. But how? It's not that straightforward. We will understand it in one of our future videos. For now, we have to know that 1 atom of oxygen combines with 2 hydrogen atoms to give us 1 water molecule. This is how atoms with different valencies combine with each other to form compounds. Now that we know how the concept of valency works, let's have a look at how the atoms come together to form independent units. Let's discuss the concept of molecules in the next video. We ended the previous video with a few questions. Let me recall them for you. How do we calculate the mass of a single atom? Is it practically possible to do so? Is there any weighing balance designed to weigh the mass of a single atom? Let us now find out the answers to these questions. Imagine we have two objects A and B. Object A weighs around 12 kilograms is what we know. But we do not know the weight of object B, and that's what we need to find. How do we find that out? We just have a weighing balance with us. Let's put them on either side of the balance and see what happens. Clearly, object A is heavier. Now if we want to find the weight of B, we will need something smaller to compare it to. So let's say we cut object A into 6 equal pieces. And now we compare the weight of object B with one piece. We see that this piece is still heavier than the object B. This probably tells us that we need a smaller piece for comparison. So let's assume we cut object A into 12 equal pieces, which means each piece weighs 1 kilogram. And now when we place them on either side of the balance, we see that it's in equilibrium. Now can we tell the weight of the object B? Yes, each piece of object A here is 1 kilogram. And hence we can say that object B also weighs 1 kilogram. Let me ask you something now. Can we say that the mass of object B is 1/12 that of object A? That's correct. This is exactly how we estimate the atomic mass of an atom. Since we cannot directly calculate the mass of an atom, we usually calculate it with respect to the mass of a carbon atom. We take carbon-12 as our standard. Wait, what is carbon-12? What does it mean? The element carbon has many isotopes and the carbon-12 is one among them. And do we know what isotopes are? Well, for now, we need to understand that they are different forms of the same element. So in the case of carbon, we will have slight differences in the atoms, which is what makes them isotopes. So carbon-12 is one such isotope which is found almost everywhere in nature. Thus, an atom of carbon-12 is considered to be a standard unit and atomic mass is thus calculated with respect to one atomic unit. And how do we define one atomic unit? One atomic mass unit is defined as the mass unit exactly equal to 1/12 of the mass of a carbon-12 atom. So let us assume this is one atom of carbon-12. We divide this in 12 exact equal pieces. We take one piece from this out of the complete unit. Can we say the mass of this single piece is one atomic mass unit? Absolutely. And this is used as a standard to calculate the atomic mass of any other atom. Some examples of this would include the atomic mass unit of hydrogen being 1, carbon being 12, nitrogen being 14, oxygen being 16, and so on. How do we understand this in a simple way? Let me ask you a question. How do you measure the mass of a person? Using kilograms, right? We say that this person's mass is 50 kilograms. Similarly, we say that the atomic mass of oxygen is 16 atomic mass units or 16 AMU. This is how we measure the atomic mass of any atom. The units used are atomic mass units. But do we know what exactly gives the atom its mass? I mean, what exactly is responsible for giving the tiny atom some amount of weight? Let us know more about the concept of atomic mass in the next video.